slide is summarizing what we spoke just before the split. Decision trees are grown by continuously splitting the feature space. Okay, the algorithm is continuously splitting the feature space. And in feature space, the tree looks like this. This is the picture we have been discussing. The same picture, if we were to look at it as a tree, this is how it would look. You know, the numbers, I was eyeballing and saying 29 and 39. They're actually 27 and 38. But essentially, there is the income split here is the root split. And on the left side of the root split is only a blue region with a little bit of impurity. And then on the right side, you split it again on age. On the left side of that split is a blue region. The right side of that, you split it again on age. And you have left side is a gray, orange partition. And the right side is a blue partition, each one with certain amount of error. So in the feature space, it looks like this. And as a tree, it looks like this. The feature space contains all the data. So this is all the training data that we are using to build the decision tree. And the divided regions contain homogeneous data subsets. Each region is only a subset of the data. What that means is that at the top of the tree, you have the most significant splits, ones that work on all the data. As you go down the tree, you're branching and branching. So you will be working on smaller and smaller subsets of data. So the lower splits are significant locally, but the higher splits near the root of the tree are significant globally. Okay, there's like the split here. Region boundaries define regions. So how do I describe, let's say, this region of orange? I would say if the income is greater than 61,000 and the age is greater than 27, greater than or equal to 27, and the age is less than 38, then this region. So region boundaries are defining the region. And every region boundary is a axis parallel check. And here, roots contain all the data in the tree. So because they are the regions that we are talking about here. The root, each root corresponds to a hyperrectangular region that is defined by the splits of the tree. So roots contain all data. Leaves contain homogeneous subsets, more or less homogeneous. The homogeneity is measured by impurity. Okay, and we'll look at the mathematical measurement in the next slide. But leaves contain homogeneous subsets. Paths along branches define leaves. Here, this leaf is defined by income is less than 61,000. Income is not less than 6. So income is greater than 61,000 and age is less than 27. That's what defines this leaf. And these happen to be the sides of the hyperrectangle. Okay. Yes, Miss Micah.
Hello. If I'm looking at the tree on the right, so as a tree, how would I know which one of the leaves has an impurity? Is it an assumption that any of the leaves could possibly have an assumption? I mean, so not assumption, but impurity.
In fact, this image is not showing it, Miss Micah. So good catch. When you use any commercial decision tree, commercial or open source standard decision tree implementation, for the leaves, you also get probabilities or counts of examples. So this leaf might say that there are 25 total samples, of which 23 are blue, and 22 are blue, and 3 are orange. That might be the split you will get 25 plus 3. So you can compute the probability of blue and the probability of orange at every leaf from those counts. This is only a simplified representation.
Yes. Okay, great. Thank you.
Thanks. Mr. Guraman?
Yeah, taking off from what Micah just said, then how would you find out, or how would we find out what is the level of accuracy or of a particular tree,
Data set. Okay.
or
So
the error
yes.
extent of?
So let's assume for now that by accuracy, we define accuracy as the label given by the tree during inference is the same as the ground truth label of that example. Let's define accuracy like that. In that case, you remember from an earlier class that we take the overall data available to us, overall supervised data available to us, divided into training set, validation tests, the validation set and test set.
Yeah.
We'll keep away test set because that's only for final reporting. So we have the training set and validation set. You build the tree on the training set. So you get this
Okay.
structure. Now you take each example of the validation set. Let's say the validation set has 500 examples. You drop each example through this tree and it will end up at a leaf. Every example is guaranteed to end up at a leaf. So the leaf it ends up at, it has a majority label. You compare that majority label to the actual label of the point. If they are the same, then you call that point correctly classified, otherwise incorrectly classified. Repeat this
Okay.
for all 500 examples in the validation set. Let's say 20 of them have got misclassified, 480 of them correctly classified. Then you know that there is a 480 out of 500, that is 96% accuracy this tree has on the validation set.
Okay.
Okay.
Okay. Right. Thank you very much.
Sure. Let's move. So there are. So now I'm summarizing the procedure on how to build these trees. Firstly, there are multiple existing algorithms that do this. ID3 was one of the original methods that triggered or sparked off interest in decision trees. This came in 1977-78 time frame. Ross Quinlan of University of Sydney and his team did a lot of work. ID3 became C4.5. The same team worked on it, and C5.0. So these are, let's say, the most popular decision tree methods. CART is also very, very popular. It's classification and regression trees. This C here just stands for classifier. ID stands for iterative dichotomizer. CART is classification and regression trees. It's a very nice piece of work that is done by researchers at University of Berkeley, Leo Breiman and team. And subsequently from CART, random forests are born. Even later, there are ensemble algorithms that that are very, very popular. Ensemble algorithms like XGBoost have a strong foundation in CART. So CART is another. CHAID is a method that has been in the statistics literature even before ID3, that a class of algorithms in the statistics literature that produce decision trees. CHAID is the way to do that. It uses correlations between different attributes to build the tree. So multiple algorithms exist. In fact, this is a very, very short list. Decision trees, there are hundreds literally of algorithms, things that give only access parallel splits, things that give oblique splits, things that have trees with one neural network at each node, a small neural network, trees which are fully grown, trees which are pruned, trees which have binary splits, non-binary splits, multiple, two classes, multiple classes, all kinds of variations exist in this, in this world of decision trees. Literally hundreds of good algorithms exist in this, in the tree family. We have already talked about recursive partitioning and continuous splitting, and dividing the data such that every subset is homogeneous. How do you split is the key decision, because once you figure this out, you need to only figure out two things. If you think about it, for building trees, you need to only figure out two things. One is, how do you split? Which variable do you split the data on? Second is, when do you stop splitting? How much impurity is okay? When do you stop splitting? So that piece is what we will talk about now. This whole thing is, how do you split? What criteria to use to split? And that's what I would like to talk about next. I talked about missing values being important, and we also talked about multi-way splits instead of binary splits. Now, to figure out how to split, let's look at impurity. Node impurity is the concept that we need to understand a little better in order to do split design. I'm just looking at the chat comments, and it's a parallel discussion going on, so I won't get into that. Impurity, I already told you, is how many points of non-majority class are there in a given region. I'm showing the regions as circles here. They're not circles. Every region in a decision tree, in a regular axis parallel decision tree, is a hyperrectangle. But just for simplicity, I'm showing it as a set, like a Venn diagram. So you see a high impurity would be, the highest impurity would be every class is equally present. Every class is equally present is the highest impurity. Less impurity would be one class is dominant, one class is present but not dominant. Zero impurity would be one class only is present. Okay, so high impurity, low impurity, no impurity. And when you know the number of points of each class within a region, you can of course use those counts as probabilities or proportions. So here we are defining that PIT is the proportion or probability of class I at node T. Let's say if the nodes are numbered, you start root node is 1. When you do the split, they become 2 and 3. Then when you split 2, it becomes 4 and 5, like a breadth first numbering of the nodes of the tree. So T is that number and I is the class. So if I take this, for example, total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 green dots and 2 pink pluses. So total of 14 points in this low impurity thing. Probability of the green class would be 12 out of 14, or proportion of the green class will be 12 out of 14. Proportion of the pink class will be 2 out of 14. That's what this PIT is. And the way you would measure the error, the classification error, there are different ways in which you can measure. There are different measures of node impurity. One easy one is the classification error, which is 1 minus max of PIT. So of all the classes, whichever is the majority class, take just that majority class. It happens to be 12 over 14 here, PIT. So 1 minus 12 over 14, that is 2 over 14. That's the classification error. So you're essentially adding up all the minority classes. If there were 3 classes here, still you could have picked one majority, one highest class. If they are equal, you would arbitrarily break the, you arbitrarily choose one of the equal classes. But you can essentially find one majority class, and 1 minus the proportion of that majority class is called classification error. So if we write down classification error here, it will be high for high impurity and low for low impurity, 0 for no impurity. Another measure is called entropy. This is a more popular method than classification error. Entropy, the equation is this. It's also again made up of this PIT, but it is minus PIT log PIT. You add it for all the classes. So PIT log PIT. Just look at this expression. Let's say that, let's take the no impurity thing, where for the green class, PIT is 1, because all 14 out of 14 points are green, let us say, or 12 out of 12 points are green. So this will be 1. Log of 1 is 0. So 1 multiplied by 0, 0 here. We need to also do this for the other class, which is 0 here. So 0 multiplied by anything is 0. So that is also 0. So the entropy will be 0 for the no impurity case. If, let's say, if you take this, points and pink points were equal. So PIT is half for the first class, half for the second class. So this will be 0.5 log 0.5 plus 0.5 log 0.5. When I do this sigma, 0.5 log 0.5. So it will be log 0.5. So log 2 to the power of minus 1, that is minus 1, because this is log base 2. Minus 1 multiplied by minus, so it is a plus 1. Entropy will be highest, that will be 1, when both classes are equally proportioned, and it will be 0 when one class is homogeneous. Entropy is a value that varies between 1 and 0. And classification error is also a value that varies between 1 and 0. You can see from the formula itself that because PIT can only vary between 0 and 1, this whole value also varies between 0 and 1. This varies between 0 and 1. Gini index is an alternative. All of these are alternative impurity measures. So Gini index is, you take PIT whole squared and do a summation over all the classes. I won't go through a calculation of this, but I hope you're able to relate to the fact that there are multiple ways in which you can measure impurity. And any of those you take and compare all the possible splits at a certain node. Let us now go back to the previous one, this picture. Let's say, imagine that these lines are not there. You're just trying to find out where to put this line. So what we do is we consider all possible splits. Let us say there are 200 points in here. Then in the horizontal, how many horizontal lines can you put? Maximum 200, because there are only 200 points. You can put one line in between every point. So there are only 200 points, 200 possible places where you can put this horizontal line. Similarly, if you were to look at vertical splits also, I'm at the root node. I'm considering splits on the variable income. I'm also considering splits on the variable age. The splits on the variable income are horizontal lines. If I have 200 points total, then I have maximum 200 possible splits on the value of income. Similarly, I have maximum 200 splits on the value of age. 200 plus 200, 400. These 400, for each of these 400, I will compute the impurity. How do I compute the impurity? Well, if I put the line here, I know how many points of each category are on the left side, how many points of each category are on the right side. So I can look at the impurity, overall impurity of that split. I do that for every one of these 400 candidates. And whichever has the lowest impurity, I pick that as my first node. Okay. So all possible splits on the variable income, all possible splits on the variable age. If there are more dimensions, all possible splits on all independent variables. And these possible splits are only discrete in number. They are not infinite. They just depend on your data set size. So across all of these candidates, you measure the impurity using any of these measures. You pick which one. Information gain uses ID3, C4 use entropy. CART uses Gini index. There are also other methods like Turing rule that it uses. CHAID uses correlation between an independent variable and the dependent variable. Correlation also is a number that can go between -1 and +1, as you know. Variance, regression trees use variance. Whatever is the measure you're using, of all the candidate splits, you greedily pick the best split and split the data with that. Repeat that recursively on both sides. Repeat the same algorithm recursively on both sides. Okay, that's how you get to the tree. I will show that visually here. There's a data set which has, yes, Mr. Hirzala.
A question, doctor. So is the objective of the decision tree is to answer a specific question or just to map out the data?
The objective of a decision tree is to describe a large amount of data using a concise model. We are model building. So, it's normally said in machine learning or data mining that you start with a ton of data, you find a few grams of patterns. So the grams of patterns that you're finding is this tree. You may have started with thousands of examples, but you have distilled it into a tree with, let us say, 20 nodes, 50 nodes, whatever. So once that concise representation of the data is there with you, then any new point that comes in, you can apply that model to predict the class. That's the purpose of decision trees.
To know where to put that new data point.
Whether they're a cheat or not, whether they are going to attend the concert or not. So
at the beginning, I was thinking that this is a way to answer a question of, is this person cheating or not?
Yes.
Well, it's not. It's just trying to explain the entire set of data.
It is trying to, they're connected, Mr. Hirzala. So the way that, the entire machine learning works like this. So that I think it's a good point. We should touch on this. Nature keeps giving us data points. Let's say beginning of 2020, we started seeing different cases of the pandemic, the COVID virus. And some measurements were made. Measurements are your independent variables, and whether the person has the virus or not is the dependent variable. Nature started throwing this data. Different people started getting sick. So after seeing some data, what you want to do is, it's not sufficient to think of each one as a different data point. You want to find a pattern. You want to find what is causing the virus, because only then you can help the new people that are coming in. So what you do is you look at this data and try to distill a model out of it, extract a model out of it. Let's say that model you extract is in decision trees, it will be a tree. In regression, it will be an equation. In neural network, it will be a black box neural network, which with some weights and neurons and so on. But whatever it is, you take this large amount of data and extract a concise and accurate pattern out of that. You know that this pattern very well represents your training data, the training data that you have seen. So you feel confident when a new person walks in to use this model to determine whether they are going to have the COVID virus or not. You can apply the model. If you are confident on it, you can apply the model on new data for doing predictions. So our goal is to predict the future. These are all predictive analytics methods. Our goal is to predict the future, but we get there by first shrinking the data into a succinct model and use the model for prediction. If it is a regular learning method. If it is a lazy learning method, You keep all the data with you. You don't build any model. When a new patient comes, you just compare their values with other patients that you know, and based on the comparison and distance, you decide whether the new patient is likely to be to have COVID or not. So there are lazy learning methods and non-lazy learning methods. The lazy learning methods, you keep the data as it is. In all the non-lazy methods, you take this route of getting a model and then using it for prediction. But our goal is prediction.
Clear. Thank you.
Okay. Okay. Yes, Ms. Raghuram.
Professor, if I mean earlier when we were using when we were passing the data through any model, we had first normalized it and then decided on passing it through any model. Will the same approach be there for this one also? Because somehow it looks like we're just splitting it as is and we are not looking at normalization.
No. We are not putting it as is. We in the way the sequence in which machine learning life cycle works is you've already picked your data. You have already put it through exploratory data analysis. You've already cleansed it. You have done your feature engineering. You do all those things irrespective of what method you're using. After all of those, and you have already divided it into training, validation, and test sets, then you decide which method. You might feed it to decision tree or neural network or nearest neighbor or whatever. So the cleansing of the data, which includes normalization, outlier removal, noise removal, feature engineering, all that is assumed to be done when we are discussing the methods.
Okay. Thank you.
Mr. Arora?
Yeah, Professor, since this is a supervised training way of teaching an algorithm or a method or a model, how do we, and in a machine learning language, I'm assuming that even in a supervised kind of a learning, you would feedback loop would be there and the model would be learning again and again.
Yes.
Now, over a period of time, is it possible that it has learned certain patterns basis which it is doing some predictability, which may be applicable to those patterns, but with new patterns emerging
Yes.
in it may not be so effective. So, how do you address that?
Yes. So, great question. And we will be covering this in good detail in the ML in practice class. That is the next Saturday class. But essentially, what you do is you keep noting exceptions in the data as the model is in inference, is in deployment. When new data comes in and your model does not perform well on, let's say, some data samples, you will put them into an exception database, store, and periodically, depending on what problem you're solving, the frequency changes. A fraud model for stockbroking may need to be rebuilt every night or multiple times a day, whereas a loan credit decisioning model may be built once every week or once every month. So frequency can change. But essentially, you maintain a database of exceptions, and then you do some intelligent sampling of, every time you redo the model, there needs to be an inertia. The previous things on which your model worked well need to continue to work well. And the new capability should be incorporated into the model. So you do some intelligent sampling from the historic data and the new data, exception data. And on that, build the classifier afresh. And do some testing with the existing data to make sure that you're still stable as a method. You're not widely going away to work well on the new samples, but failing on samples that you already worked well on. So we ensure that such oscillations are not there. So with some inertia, you periodically rebuild the model. And these are fast algorithms, so it's okay to rebuild. These are not like training an LLM. So, they lend themselves to repeat building of the classifier. The trick is in maintaining the right data set to build the model.
So this is a continuous process, a
Yes,
lifeline process, which you have to kind of
absolutely.
rebuild the models and on the fresh data.
Yes. So you imagine that there are two lanes. One lane is the deployed model. It is continuing to work. But in the second lane, there are time instances where you replace the model in deployment with the new model, and you keep doing that at some frequency.
Thank you.
Yeah, sure. So here we are showing, the root has 200 samples of 3 classes. So proportions are given here. Based on that, if you were to look at, the classification error, I'm taking the impurity measure as the classification error here. Majority class is 0.5. So 1 minus 0.5, 0.5 is the impurity here. Because there is an impurity, we must split. So when we split that, when we find the right split, and how to find that, I already mentioned, you go through different splits, look at their impurity, and then let's say that this is one particular split where this 200 is being split into 150 and 50, and the counts are given here. On one side, it becomes completely homogeneous because you only have points of class 1. So it has impurity of 0. Okay. The calculations, it's the same as what we did before, 1 minus the majority class. Majority class here is 1. So you have a 0. And on this side, it's 150 points divided into 3 classes. You have their proportions. So impurity is 1 minus highest class, so 0.33. Since it's 150 out of 200 points, 150 out of 200 multiplied by 0.33 plus 50 out of 200 multiplied by 0 impurity. Total impurity of this split is 0.25. And this is one split, which divided the 200 into 150 plus 50. You now move that line, let us say, along vertical axis, and let us say this becomes 155 and 45. They will have different numbers here. Based on that, you compute the goodness of that split. Keep doing that for every split, and at the end, whichever splits gives the maximum number here, maximum utility of that split, you pick that as your root split. So every split you compute this thing, here it is classification error. It could be entropy, it could be Gini index, it could be variance, it could be correlation, whatever is your measure. For every split, compute that and pick the split that has the highest value. That's how these decision tree algorithms work. The second decision is when to stop splitting. There are different ways. Either you stop when all the nodes are pure, homogeneous leaves, or you stop, you grow to a certain threshold and prune it, grow completely, and then prune back the tree. Okay, this one I hope you're able to see. We keep dividing the space until we get completely homogeneous hyperrectangles. But then some hyperrectangles are not adding much value, because if there are a million points in which one small rectangle is dividing 2 points, that 2 points may not be adding much value to the overall tree. So after building the whole tree, you know which branches are less useful. There are mathematical measures to compute. So using those, you get the goodness of each of the nodes and cut some branches. So prune it back, prune the tree back. Then you have a few impure nodes, but overall the tree has much better generalization accuracy. Because if you go all the way down to pure leaves, you are overfitting the training data. Pruning helps reduce overfitting and increases accuracy on the on the validation data. So you could stop early, or you could prune. Stopping early is putting a threshold on the information gain. If my split does not add more than this value, then I don't want that split. If my best split does not add much information, then I might as well leave the impure node as it is. So it could be an early stopping criterion, or it could be growing and pruning. And the purpose of this pruning is increasing the generalization accuracy, reducing overfitting. A tree in real life would look like this. This is a visualization of visualization of a tree. In addition to things that I have already pointed out, like tests and leaves and root node and so on, a few more things you can see here. We have a distribution of classes, different classes. So this leaf is purer than this leaf. This leaf seems to have multiple classes equally represented. And the number of points, there are 5,042 points here, 16,385 points here. You take that, let's say, a certain number of points and keep splitting. So when you come to the leaves here, still you might have a large number of data points at the leaves as well. This one has 472, but this one has 24,000. In fact, the 472 is an impure, because multiple classes seem dominant, whereas a single class is dominant for the 24,000. So I hope you're able to see that we built essentially a binary tree, but it is possible to have trees that are very, very large. And you also show, the information gain, how useful was a split. You can show it using color. So the color coding is essentially showing how good the split was. Yes, Miss Micah.
Is this something that I would use, or we could use on the back end, just as supporting documentation of how we got to certain data? Or what I'm thinking is, like, I'm an executive and someone brings that to me and I'm like, what in the world am I looking at? It's so convoluted. There's so many directions. How would I use something like this? Because that kind of,
Yes.
overwhelmed
Yeah,
my nervous system.
yes. Yes, I totally relate to that. Thank you for pointing that out. So firstly, visualization is for the human. The system builds the tree, can use it for classification in practice, and that cycle does not need you to overload the nervous system. Whereas at times you want to know what the method unearthed as a pattern, the decision trees method, what did it unearth from your data as a pattern is what you are asking. So, for example, you work for Amazon, you handle their, let's say, weekend purchases of books, let's say. So there are a few million people over the last 1 month who bought books over the weekend, few million, a few tens of millions, and a few tens of millions that didn't buy books. And this entire data, you give it to your decision tree method and ask it to find useful patterns in that. So it builds a humongous structure like this, let's say with about 5,000 nodes. Now, you want to identify which are the nodes here that will give me a business insight. And you will look at the ones with the highest information gain, the splits that have given you the highest information gain. You will go and see, how do I know whether somebody will buy a book on the weekend or not? Which variable is giving me this? Is it their age? Is it their location? Is it a past purchase that determines it? Is that even predictable? Whether they will buy a book this weekend or not? Questions like these about your data are answered when you study a model that has been extracted from the data like this. Instead of going through tens of millions of data points, it's easy for you to go through. Let us say, even in this tree, I will subtract all nodes where, let's say, multiple classes seem to be represented. Say when there is a single peak like this, it is a pure node. When there are multiple classes that are high, that have counts, then it is an impure node. So even if you, for example, look only at the purest nodes, all zero impurity nodes, and look at what variables are helping you get there, what tests are helping you get there. Like, for example, even though I may have millions of data points, to get to these 22,000 points, it's just 4 tests. And with these 4 tests, I'm able to do a clean separation of 22,000 customers, just 4 attributes. So when you as a business manager look at those 4 attributes, whatever these mean, POS, actually 3 attributes only, POS, MZ, and PMZQ, whatever those attributes are. I'm just putting a sample tree visualization. So I don't know what those attributes are. But you as a manager will be able to see that just with 3 attributes, I can cleanly separate 22,000 customers and understand them. That's the value. And you can see the same thing here. I mean, 10,000 people, different, that's the point.
Okay, thank you so much.
Thank you. Increased synthetic data. Mr. Huggins says, Professor, we are moving into the age of increased synthetic data. How will this new form of data affect models going forward? Synthetic data is definitely useful even for symbolic machine learning methods, Mr. Huggins. You just need to make sure that it is there's a sophisticated model that is generating that synthetic data. It cannot be a simple machine learning model generating that data, because then the data itself will not have any depth. For example, if I want to have a synthetic data of pediatric oncology patients, it's a very specific category, pediatric little children who have cancer. There is a very, there's a lot of oncology knowledge, lot of human physiology knowledge, disease knowledge that needs to go into building synthetic data examples of a domain like that. So assuming that you have a sophisticated synthetic data generator, it is very useful for symbolic ML methods also. It's anyway for neural networks, we will see when we study them that they are data guzzlers. They need a lot of data. So synthetic data becomes important for them because natural data may not be available. Whereas with these symbolic machine learning methods, they many a time can work well with lesser data volume. So synthetic data usage is less prominent here than it is in neural network, deep learning networks. However, even here it will be useful. What is important is to have a sophisticated synthetic data generator. Okay. Then if we choose the least impure node as root, is it guaranteed that the tree won't be skewed on one side? No, it's not. It's actually a greedy decision you're making. Sometimes, depending on the data distribution, you can get very skewed trees, even if you choose the least impure node, Mr. Bhaskaran. And Mr. Shibaba says a decision tree helps visualize how data is repeatedly split into smaller, more homogeneous groups, branches, color, leaves. In general terms, a good decision tree keeps splitting data so that each final leaf contains mostly similar examples. Absolutely correct. Thank you. That's all I want to say on decision trees. Are there any pending questions? Otherwise, I hope you have some understanding of what decision trees look like and what their corresponding geometric, intuition is, and why we use decision trees. I hope you have high-level answers for these 3 aspects. If you have any questions, we can address those, and then I want to use the rest of the time to on neural networks. Okay. Please feel free to go back to a question if you remember something. So now the decision trees we'll put aside, because like I said, both of these are separate methods. We want to use the next 25 minutes to get started with artificial neural networks. Like I said, I'm not too worried about getting deeper into practical applications of neural networks today. I just want to give you an intuition of what they are as a model. Much more depth we will go into in future courses, particularly the deep learning course. We will dig into neural networks for 15 sessions. Firstly, this undoubtedly is the driving force for automation of the future today. I mean, we are at a inflection point for neural networks. There are literally, trillions of dollars of funding that is being put worldwide on improving neural networks for different problems. What I have on the slide here are some applications where neural networks are used. All the way from financial fraud to recommendation systems, to predictive maintenance in industry, to image recognition, as in, let's say, biometrics or face recognition, to creative arts, to autonomous vehicles, to all chatbots and everything. All are based on artificial neural networks. Hence, it is important for us to know what they are, how they came about, approximately how they work. That's my scope today. Unlike any of the methods that we have seen so far, we have seen, just to a very, very quick synopsis, we have, in unsupervised methods, we looked at clustering, we looked at time series, we looked at collaborative filtering, association rules, and in supervised methods, so far, we have looked at regression, linear and logistic regression, k nearest neighbor, and decision trees. Unlike any of these methods, the artificial neural networks are motivated by biology, motivated by real world intelligence. None of the others that we have seen so far is motivated by biological intelligence. They are more engineering solutions or mathematical solutions, where the goal is, let's build a learning system. We don't care how. But in artificial neural networks, let's study the intelligence around us. Let us approximate it into a system. Let us model it into a system, maybe with some simplifications, and then let us use that to build intelligent systems. So the intelligence around us, which is the motivator for artificial neural networks, is biological intelligence, particularly biological neural networks. Animals are able to adapt, and they can use their nervous system to perform adaptive behavior. They know when to run, they know when to, fight or flight. They know what to eat. They get used to a new environment, etc. And hence, and the insight is that if we can mimic the nervous system, which is brain, neurons in the spine, neurons in other parts of the body like the retina, I'm adding all of that into the nervous system. So if we can appropriately model the nervous system, we should be able to produce intelligent behavior in artificial systems. This is the driving hypothesis behind artificial neural networks, that we see intelligence being demonstrated around us. That intelligence seems to be coming from brain and nervous system. And so if we can model that brain and some part of the nervous system into artificial systems, then we can see intelligence here also. That's the motivation. Nervous system, the next observation is nervous system is built using relatively simple units, neurons. Hence, copying the behavior and functionality of a neuron should be a good start for us to build machine learning. That is what is the starting point for artificial neural networks. A biological neuron looks like this on the right side. I just took this off of Wikipedia. It's a complex thing. However, essentially what it does is receives inputs from multiple connectors, does some computation or some mix-up of that information. This information that is coming in are electrochemical signals. Some integration of that information happens here, and the integrated information passes through axons to the next neuron. Okay, this is the next neuron. So it is essentially, a neuron is essentially a electrochemical information integration unit. So fundamental units are neurons. Connections between neurons are called synapses. Mimicking, I'm sorry for the lack of K here, spelling mistake. Mimicking their behavior and functionality is a reasonable approach to build ANNs. And the intelligence seems to come not from an individual neuron, but from network of neurons. So the adult human brain consists of 100 billion neurons and 1,000 trillion synapses, 1,000 trillion connections between the 100 billion neurons. It seems that even though one neuron is a very simple structure, it's still much more complex than an artificial neuron. I will show artificial neuron. A natural neuron or a biological neuron is much more sophisticated than an artificial neuron. But even then, it's a simple entity. Enormous intelligence, general intelligence, can come from taking such neurons, a large number of them, and connecting them up. Obviously, there needs to be a rhyme or reason to connect things. There should be a method in the madness of connecting these 100 billion neurons. So we also want to learn what is that method? What is the right way to connect them that will work? How should we not connect them? We need to look into all of that. But for now, neuron is a simple thing, and we want to mimic the neuron, and we want enough compute to take millions or billions of those neurons and hook them up. Okay, in some ways. The second observation, biologically, we want to give biological observations first, and then we'll jump to artificial neural networks. The second observation is that neurons seem to be arranged in a hierarchical manner. Different groups of neurons connected in hierarchical ways seems to be doing different functions. So I'm taking the example of the visual cortex in the brain here. And this is the retina, somebody's eye. Signals, retina itself has some neurons. So it is the detecting some information, visual information. And that information gets processed through a bunch of neurons called LGN. And then goes through this hierarchical sophistication, V1 to V2 to V3. Here I'm drawing the same thing, as an artificial neural network, deep learning network. LGN from retina. Retina is a bunch of neurons. Some signal is collected. Then it goes through this LGN. don't worry about what LGN is, biological terms. From there, it goes to V1, neurological terms actually. From there, it goes to the V1 layer, V2 layer, V3 layer, and so on. And at every layer, I mean, V1 layer will detect very small patterns, like simple lines or simple color bands. And V2 layer will combine these lines into shapes, small shapes like rectangles, triangles, etc. V3 will combine many triangles into, bigger shapes. And then there is a detector, LOC, that says, oh, this is a cat. Okay. Every individual line or a fiber or a color variation from the image is, it falls on the retina. I'm still talking about only biological neural network, not artificial. I'm just showing it as layers so it becomes simpler. In actual terms, it looks, I mean, these are different areas of the visual cortex. So three things. There's a neuron, which is a simple computational unit. Many such neurons, when they are connected, seem to give rise to very intelligent behavior. The connections seem to be hierarchical. These are the three biological observations we have made so far. Connections between neurons seem to be hierarchical. The other thing we get from nature is that more neurons seem to be indicating more intelligence more often than not. There are exceptions, but more often than not, more neurons seem to be indicating higher intelligence. So I'm listing a few life forms, from a nematode worm that has 300 neurons, to a snail, to an ant, all the way to humans, whales, elephants, dolphins. And the number of neurons, increase orders of magnitude as we go. So if you take an ant, it's operating with about 10,000 neurons. Fairly decent intelligence with 10,000 neurons, right? Knows its environment, can do social work, remembers significantly, can find its food, can manage to balance a weight that is many times its body weight, so on and so forth, with just 10,000 neurons. And then when you go into, 10 million neurons, which is the bat here, it's able to navigate in the dark. It's able to, travel longer distances than an ant does. It's able to fly. It's able to, live on a tree, have various things. It has complex functions. So from 10,000 to 10 million. And then when you come to humans here, you're 100 billion. 10 to the power of 9 is a billion. So chimp is in the billion range. 100 billion range are the humans. And we have metacognition. We know, we think about thinking. We have awareness. We have multiple other things. I mean, some of you might ask the question, is all that, awareness or metacognition, other than regular tasks that we do, is that coming from the brain? And that's a valid question. I don't know the answer to that. But brain seems a good part of the work. So we start with the brain. In human body, I think intelligence just doesn't reside in the brain. But then brain is doing a good part of the work. So it's not a bad place to start our exploration. And looking at a table like this, it appears like more neurons means more intelligence. Exceptions, a bat can have much better vision than a human or a whale. I mean, human or an elephant. A honeybee may be able to see more electromagnetic range of radiation than somebody, a much larger animal may see. So individual capabilities may be more for these smaller brained entities also. But in general, the trend seems to be more neurons, more intelligence. This is directly reflected in what the LLM market is doing now. There has been, from small neural networks, like when GPT-2 came out, from then till GPT-5, there is an enormous increase in the number of parameters. Parameters are nothing but interconnections, synapses. Approximately, when we say that something is a 7 billion parameter model or a 70 billion parameter model, we are saying that there are 70 billion synapses, approximately. So in order to have more interconnections, you do need more neurons. Of course, the number of neurons will be still small. It will not be 70 billion. Even if you have a few 100,000 neurons, if they're all connected in complex ways, you can get to billions of interconnections. So there has been a steady trend from 2012, when deep learning started in the earnest, till now, about 15 years, 14, 15 years period, there is a clear increase in the number of neurons that we are using. However, now we seem to have reached a point where we say, okay, we have general systems like the frontier models, which have a lot of intelligence, trillions of parameters, but we don't need all of that for every task. So let's also shrink and make small language models and micro language models and mini nano language models, which are good enough for certain purposes. So we first created humans and whale equivalent of LLMs. And now we are going back for specific functionality, small drones that need to do autonomous flying into an enemy territory and do something in a war and come back, probably requires much fewer neurons, and hence much better energy efficiency, much smaller data requirement for training, much smaller carbon footprint, power needs, all that. So here we seem to have quickly gone to this in about 14, 15 years, and next 5, 10 years in the generative AI space, you will see a walk backwards where specific intelligence will be created with much smaller neuron base. Okay. To agree to that argument, we need to also know that even with smaller number of neurons, you can do sophisticated intellectual work. If I say that a honeybee flies well, remembers 100 different gardens for its honey, that's one thing. But intellectually, honeybee is not doing much. So people have done experiments on intellectually how much can be done by small systems with, biological entities with smaller number of neurons, the species with smaller number of neurons. Here, if you take a bird, let me see where the birds are, bat, maybe even less. So about 1 million, 10 million neuron type, that kind of complexity. A pigeon, people think that pigeon is not very intelligent. It's a common expression, pigeon brain. So Watanabe and his team did experiments where pigeons were taught to differentiate between Van Gogh paintings and Chagall paintings. So not just recognize a painting when it sees. If it sees earlier, it sees again, it should recognize. But not only that, from the paintings it sees, it abstracts out the artist's painting style. How do Van Gogh paintings look? And then when a new Van Gogh painting is shown, it correctly recognizes that. So 95% accuracy on images that it has already seen, 85% accuracy on images it has not seen. So very good abstract understanding of an artist's style is possible for pigeons. This is something that neural networks researchers initially were looking at what is possible with smaller number of neurons, and this is one of the interesting experiments of that era. There are other experiments like mice, how they can, even if there's a very large maze, a mouse can memorize the maze completely, remember the order of contraband drugs or explosives, and then help us find them. So small, and mouse, like we saw, a mouse is here about 1 million neurons. So point is that with 1 million neurons you can do fairly impressive cognitive tasks as well, not just survival tasks, but cognitive tasks. Because survival, one can argue that it didn't learn. The species learned, and that already exists as a hard coding. But tasks like these, individual pigeons and mice are taught, and they learn. So we have said a few things. Let me very quickly say, neurons are the basis of intelligence. You need to model a neuron. Then you need to get many such neurons together and connect them up. There is a method to connect them up. The nature seems to do it hierarchically, so we should look at that. Even with a small number of neurons, you can do fairly good cognitive tasks. After seeing all this in biology, then artificial neural network researchers went into creating these artificial mathematical models of neural networks. And that's what we are showing here. If this is a biological neuron, this is the equivalent artificial neuron. Biological neuron also gets signals from multiple inputs. And some signals, these are electrochemical inputs in biological neurons, just electrical inputs or data inputs in the artificial neurons. Each input may come at a different strength, so that's modeled as a weight. The neuron itself may have some bias, which is modeled as this bias term B. Integration of the input signals happens at a neuron core, at a cell, in a cell. So that is the same thing that happens here. In a neuron essentially does a weighted summation, W1x1 plus W2x2 plus W3x3 plus B. It does a weighted summation of signals that are coming into it. And then it applies an activation function to it. That's what this F is. F is an activation function. And it applies some threshold to that. And then the signal that goes to the next neuron is decided by this simple mathematical calculation. A summation, an activation, and a thresholding. That's how a neuron is designed. And Marvin Minsky and his team were one of the first ones to design this. They called this the perceptron. Instead of calling it, this is a neuron, this is a perceptron. The perceptron, if you go a little deeper into it, is unless you make this a nonlinear function, it becomes brittle because of this threshold. Whenever you have a threshold, there is a discontinuity that makes the math brittle. So what we do is we don't just put a threshold, we put a activation function which is continuous. This is the thresholding function. So there's a discontinuity at x equals 0. But this is a sigmoid variation of that function. So it's called a sigmoid activation function. And this is a continuous function. This is discrete. So this is less brittle than this. So a perceptron becomes a sigmoid neuron when you introduce this function to it. To summarize that, and I'll stop with this slide. To summarize, this is how one artificial neuron looks like. So you have some inputs that are coming into the neuron. Each input has some weight. This weight can be positive or negative. It's a real number. It cannot be complex or anything, complex numbers. It is just real numbers where you can use that in multiplication, positive or negative. It need not be between -1 and +1. It can be any weight. You do that summation, and in a neuron, you add a bias term to it. Bias also has a weight. So you can learn how much importance to give to the bias term. That's what this is. Things in white circles here are all weights that the neural network will learn. This is the bias term. These are the input terms. Pink is the input terms. Blue is the bias term. All of them get added in the body of the neuron. So neuron is nothing but a summation equation. In fact, a matrix multiplication equation, because it's W1x1 plus W2x3, x2 plus W3x3, like that. So it's two vectors being multiplied, dot product of two vectors. That's what is a neuron. So neuron, really, in artificial neural networks, there is no neuron that exists. Right? In physical body, neurons are things that exist, which can do electrochemical reactions. In an artificial neuron, all you need is a function computation. So it's just some compute. A single piece of compute can have billions of neurons modeled inside it. Okay. So I hope that makes sense to you. Weights and bias are, inputs and bias with certain weightage are summed up, and then an activation function like sigmoid is applied to it. Sigmoid is one option. There are things like ReLU, TANH, softmax. There could be different types of activation functions. So the purpose of this, you can see that up till this point, W1x1 plus W2x2, etc., is a linear function. So up to this point, it's linear. This is where it becomes nonlinear. So without the activation function, a neural network does nothing other than a linear regression. Individual neuron, it's just a weighted summation like a linear regression. What gives it the power is this activation function, because it allows you to get nonlinearity into the learning. So activation function. Yes, Ms. Luo. Did you have a question, Ms. Luo? Okay. So the activation function is what gives it the nonlinearity. When you do all of that computation, what is going in are continuous inputs. Just like into linear regression, continuous inputs are going into a neural network also. Continuous inputs only can go. You might ask, we have such neural networks which are working with language, which are working with images. What is the continuous thing that's going in? The continuous thing that's going in is called an embedding. So an image is converted to an embedding. A text is converted to an embedding. Embedding is a real valued vector. Only real valued vectors can be processed by neural networks. And what a neuron produces is also a real value. On this, there could be a threshold optionally, or it can directly go into the next neuron. And then there is a whole network of neurons that happens. I will talk about networks and learning in artificial neural networks in the next, beginning of tomorrow's class. But this, now what we did is, from biology came to one artificial neuron. That's the journey we completed. Now from one neuron, we have to go to a neural network, which we will do tomorrow. I'll pause here. I'll be happy to answer any questions. Thank you, Mr. Shivaba. Good description. Yes, Mr. Rakesh Kumar.
Yeah, sir. Good evening, sir.
Good evening.
Sir, here we are talking one neural network, and there are function activation, and output is very low as you show in the output 0.27%. Uh, then
Not percent, just a number.
a
0.27.
number, just a number. I want to know that why is this number is low? If you can elaborate.
Yes. It's just an example we are showing. That could be a high number as well. So for example, if you're, what seems to be happening here is two inputs are positive and two inputs are negative. So they're canceling themselves out. That seems to be what's the reason for the smaller output here. It's essentially a simple mathematical function, Mr. Rakesh Kumar. So it is possible that a neuron produces a very high amount of output. It's also possible that it produces a very low output. This is there are terms for this. So your gradients can disappear, which are called vanishing gradients, or it could be exploding gradients. We'll look into all of that in the deep learning class. I don't want to go into those complexities now, but for now, the difference between a human neuron or a biological neuron and a artificial neuron is that biological neuron has much stronger um,
Accuracy.
normalization mechanisms.
Yeah, yeah.
So
And and accuracy also.
it won't let a very strong electrical impulse go through the brain because it will burn the network, right? So we have much, subdued, and this is also low power for low power reasons. With 30 watts, if we want to run 100 billion neuron, 1,000 trillion synapse network with, a few watts, then you necessarily will have very simple, very small signals going through it. And it should be very, very accurate. Whereas in artificial neural networks, we have not gone to that yet. And hence, you can have large inputs here. You can have very small inputs also. So this is just this is just an example.
Okay, thank you, sir.
Thank you. Any other questions? Okay, so let's stop here. To summarize, we have gone through decision trees today, and then we did up to a single neuron. Neural networks will finish tomorrow, and primary topic tomorrow will be ensembles. If there are no other questions, we can wrap up for the day. Thank you very much for your attention.
May I ask
Yes,
a
sir.
question, please?
Thank you.
Yes.
Thank you very much, Professor.
Thank you.
Thank you, Professor.
Thank you. Ms. Raghuraman,
Thank
please
you.
go ahead.
Thank you,
Thank you,
Professor.
sir.
I was just
Thank you.
wondering about the sigmoid curve. Does
Yeah.
it, if it is the human brain and